The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
Thank you very much. It's my great pleasure to be here. It's my first time in Brazil, and as soon as the slides start, I will be in. Let me first begin by wishing you a very good afternoon and adding my sincere thanks for organizing this topic and for allowing us to share for a few minutes some thoughts about innovation. And in particular, I wanted to make the story a little bit personal. I started at MIT as a professor, primarily interested in chemistry and spectroscopy. Never thought that any of my inventions would directly lead to something commercializable. But what I found at MIT is there's a culture and a system of innovation, we can call it an ecosystem, that really leads you towards that path. And it's a very exciting area. So I will share with you in my role as Associate Provost a few minutes of talking about this ecosystem and its main components and what we're doing to try to enhance it. As Carl Koster said, we're never satisfied at MIT. And I will share with you then a little bit of my personal journey about two of the companies that I've founded and some other basic technology, because it's not only the idea of entrepreneurship, but it's also the idea of continuing to add to the basic science and engineering portfolio that allows you to be innovative. So I'm sure most of you are familiar with MIT, and really there's a great emphasis on basic research at MIT, and Carl shared with you some of the metrics about this research. Much of this is in our science and engineering departments, but we also have an outstanding school of business, which is really important for innovation. And we find also increasingly that our School of Humanities and Social Sciences and also our School of Architecture and Planning are essential as we think about moving these innovations into other parts of the world, and also especially into cities and their organizations. So let me show you a little bit about our local ecosystem here. This is an aerial view of the MIT campus. We do not have nearly as many tall buildings as you have here in Sao Paulo. But I wanted to show you, I think, what was really important when MIT came to this location in 1916 is that the initial buildings were all connected in this U-shaped enterprise that faces the Charles River. And all of the engineering departments were put together. And the fact that you could walk from one department to another without leaving the building really began this culture of interdisciplinary discovery, because all of the growth is really mostly at the boundaries. I myself personally have a research paper with someone from every department of engineering at MIT. And we're continually renewing ourselves. The building in here shown in white is not yet built. It's currently a hole in the ground. We took out an old building, and we're really continuing to invest heavily in nanotechnology, and I will tell you about that. The other part is that we're very close to Boston, and in particular, some of the famous hospitals like the Massachusetts General Hospital, and that has helped us to be innovative in areas of medical technology. So it's not only the campus ecosystem, but it's our neighbors directly near us. And recently we've been finding that companies that you would normally associate with other parts of the country, like California, are moving to Cambridge to be co-located with MIT. And I particularly like this quote from the head of Google Boston. And despite our talented neighbors, our talents in Silicon Valley, what they're finding here is that there's something about the MIT talent that's really attractive and important for innovation. So one of the other things that MIT does very well, we showed the buildings were interconnected. Also, the administrative structure is interconnected. And our students are very excited about working on global problems that will have an impact. And we're organized not just by departments, but by innovation initiatives and centers. One of the very earliest example of this is the MIT Energy Initiative, and you will hear from Bob Armstrong, the professor of chemical engineering, who has led this and is really important to connect all of these disciplines and industry. Newer are initiatives on innovation and on sustainability, healthcare, thinking about how data and society intermix. And we also have a very large program on digital learning and bringing some of the courses that we have at MIT to a broader audience around the world. And as we're talking, MIT is the center of this ecosystem in innovation, and I just wanted to give you some examples of that. We're surrounded physically by companies which have been started by MIT faculty and alumni, and that entrepreneurial spirit is in the blood. In addition to the students and researchers working on campus, there's experienced entrepreneurs, risk capital that funds these activities, as well as government agencies that are co-located with us. And I like to think about all of these things as having porous borders so that the ideas from one sector really bleed into the other, and there's really a back and forth exchange which is essential in having this innovation ecosystem. So here's a map. You saw the aerial view of campus and the Charles River, so you can see the Charles River here. Everything that's in this triangle that's mostly yellow are actually our academic buildings on campus. And then you'll see that we're physically within walking distance of all these other companies. The blue buildings represent bio and pharma, which are some of the most represented industries on campus, and you will see companies that you recognize there, like Biogen and Genzyme and Novartis. We also have companies that are IT and data. We saw the Google office, also Amazon, Microsoft, and Facebook are also typically thought of as California companies. Well, now they're also next to MIT. And to get that spirit and also to have an advantage in hiring people. Because of the energy initiative, we have companies in green, which represent the forefront of energy technology, includes Schlumberger on Saudi Aramco, and you'll also see that we have venture capital here. And this map really needs to be updated. We've had several changes since then. So it's really this mix of talent, resources, and proximity that leads to the innovation environment. And although we have this focus on our local ecosystem, we really like exploring the rest of the world and understanding what the rest of the world has to teach us and where technology that we may have can impact the world. And we already have significant relationships with Brazil, but this map shows you all the other countries in the world in which MIT has active research partnerships. And this global network is very important to us, not only for our sponsorships, but many of our alumni are international, and so we're looking to have a global impact. As we mentioned, the R&D total for MIT is almost $700 million in fiscal year 2014. It comes from a variety of sources, and for me, one of the most interesting part is that 19% comes from industry. And usually industry brings more than money. They bring the market know-how in this area, and make sure that we're solving problems that are important. Just to show you some of the impact, we're very concerned about patents here. I'm not sure, this animation didn't work exactly correctly, but there are basically over 20 patents a year that are filed and licensed and lead to startup companies at MIT. We're continuing to invest in the very initial stages of innovation. There's MIT Nano, which is a new building that's being constructed. It will be the world's largest university nano fab. It, again, with that ethos of being connected to all the science and engineering departments on campus. It will really have open spaces where innovation is on display. And we need this continued type of investment in the basic research to keep us at the forefront. Our collaboration in this will not only be with MIT, but we have enough ability to host people from our international collaborations, and we can accommodate over 2,000 innovators per year in this state-of-the-art building, which will be completed in 2018. We're also continuing to think about how to innovate in terms of our structure. So I talked about interdisciplinary work, working with another department in the same school. I'm in the School of Engineering at MIT, but we're also thinking about working across schools. So here's an example that's thinking about how we relate to medical research at MIT. It involves collaborations between our School of Management, our School of Engineering, and our School of Science. And it looks at all those partners that are surrounding MIT, the very important hospitals that are across the river, industry, and our neighboring university, the Harvard Medical School. And we're really thinking about how we can go faster and what are the grand challenges in this area. How do we bring an invention to our partners? And we can't wait to have the invention finished before we start thinking about this. There really needs to be an overlap in terms of what are the basic questions to be asked, what is the invention, and how is it then deployed for commercial impact. Here's my patent slide. Sorry about that. We're a little late on that. So this is my final slide on basically the overview for MIT. We really think about technology in stages going from that initial innovation to where we hit high growth commercialization. And we're interested in innovation pathways that go through entrepreneurship and risk capital, as well as direct licensing to large global corporations. And our innovation initiative brings together things that we've had at MIT for a long time. So let me start by talking about the global corporations. It's very important for us to have a technology licensing office, which allows us to have the patenting and licensing opportunities that we have. Essential is the MIT Industrial Liaison Program, which is the sponsor for this conference and really is a catalyst for bringing many new companies and partners to MIT. And we also have a Deshpande Center in which large companies invest and really get to see a very early view of what are the new technologies coming out of MIT. And then we have people on campus that are really interested in taking the technology. Although it's possible for large corporations simply to license a patent and work on the technology themselves, we really find that it's people that transfer technologies. So it's when that innovator who has gotten the patent is involved directly in the tech transfer with the large company, or in fact, gets together and actually starts a small company, which then the large company can work with. This is when tech transfer really happens. And we have many, many cases of, we're trying to put it together so that it's formalized in an important way. So some of the things besides we've talked about the Technology Licensing Office. We have several student competitions, the Lemelson Prize and the 100K competitions. And these are a combination of both educational activities, they're sort of hands-on projects with a competitive arena that grow every year. There's more and more students, both undergraduate and graduate, that participate in these every year. There are also formal classes. We have I-Teams, which is joint between the School of Engineering and Sloan School, which vets many of these ideas about how to do technology. And we also have a venture mentoring service where people who have been successful entrepreneurs have a chance to come back to campus and mentor those fledgling companies that want to be them in the future. And putting all of those together is really essential to have this innovation ecosystem. So that's sort of a very high-level view of all of the activities towards innovation at MIT. And what I'd like to spend the rest of the time here is to share a little bit of my personal experience as a chemical engineering professor, and how this led to some formation of companies and innovative technology. I'll first talk about the technology in my lab. I'll show some very technical things, and won't discuss them in great detail, but just to give you an idea that it really does require deep technology in order to make the kind of innovation that we would like for the future. We can't just take things that people know and take them off the shelf and put them together and get everything that we need. I'll talk a little bit about the first company I founded, GVD, which has been fully commercial and profitable for over a decade. I'll talk about a new company that was formed in the past year, Dropwise Technology, and I'll show you an example of one of my PhD students who ended up winning the Lemelson Prize for new technology. So you'll start to see the pathway sort of in reverse during the rest of this talk. So the basic technology I work on is called chemical vapor deposition. It's well known in the semiconductor industry, mostly for making inorganic materials. But my interest is actually in making organic materials because they have very interesting properties in controlling surface, chemistry, and making flexible devices and patterns. And this is the cover of a book that just came out this year, which I've edited on the topic. And polymers are very common material, and the most common way if you wanted to make a thin film of a polymer would be to dissolve it up in some liquid and cast it onto a surface that's often spinning, called spin coating. But as we get into microtechnology and nanotechnology, there are some problems with this approach. The liquid itself has surface tension, and it doesn't coat these structures very smoothly. And you can see here some of the defects, that the polymer film just lays on top of the surface and leaves gaps. It forms meniscus, and so it doesn't really protect the surface, and you can't build devices like you would like to do. And so if we take an alternate approach, instead of making the polymer and putting it in solution, we instead, in the gas phase, take a building block of the polymer, a monomer, and have it absorb on a surface and just react, we can indeed get this coverage of microstructured surfaces. So you see here in this trench, which has micron-sized dimension, that the vapor deposited way that was pioneered by my lab is able to coat every nook and cranny of the surface. And we call this so-called conformal coating. And you can see that the traditional liquid way doesn't coat at all the bottoms here. There's just a bridge across. And so making a different process actually helps you get different attributes for these polymer coatings. So that was a micron scale example. Let's go down to the nanoscale. I'm sure you're familiar with carbon nanotubes, and people like them for their mechanical strength. And Professor John Hart in the mechanical engineering department at MIT is able to make these very great patterns that are, if you look at each post here, there's thousands of carbon nanotubes here. And these would be very strong for patterning. But what you'd like to do is then apply an ink and be able to make these patterns. However, when you apply the ink, that surface tension causes the posts to collapse on one another. Quite beautiful structures that are made, but are not very good for reproducing this as a stamp for devices. And so really with this, we have a competition with these carbon nanotubes between the force that's generated by the liquid, the capillary force, and the elastic force of the carbon nanotube themselves. So let me show you with a movie the difference. So if we just make the carbon nanotubes and don't treat the surface with CVD polymers, then as we're drying solutions like the ink, you can see the carbon nanotube posts. At first they're fine, but as the liquid evaporates, the capillary forces start to dominate, and you can see that the structure of the post changes, and really quite dramatically at the end. Now instead, if we apply a coating of our CVD polymers to these carbon nanotubes, we can reduce the effect of surface tension because of the low surface energy. And now when you dry the ink, you see that you're able to retain the dimensions that you want for patterning. And indeed, with these stamps, then you're able to produce very cheaply and economically all kinds of patterns that you would want for devices without traditional lithography. So this is to try to give you an idea of the technology and why your approach makes a difference. So we've actually really invented two different techniques that make polymers, depending on the type of polymer that we want. It's not our intent to compete with traditional solution polymers, but really to focus on polymers that would be difficult to dissolve, things like fluoropolymers or cross-linked networks. And we've spent a lot of time really trying to understand these processes. So this particular graph is to show you some data and the fact that we have an experimental, very good experimental control, as well as a theory to explain exactly the solid line that's here. And this took quite a bit of work. We're really working with one particular polymer. But the value of this is then twofold. We understand for this graph how to put the axis at the bottom in a so-called dimensionless form. And so then this tells us how to do additional monomers. And in fact, while this was made for one monomer, we now have demonstrated over 70 different polymer compositions that work. And we were able to do that very quickly because we spent so much time on that first composition. And this is an example of the many different types of polymers that we've been able to do by the chemical vapor deposition mechanism and the many different properties that they have. And the ability to make this advance to so many different materials relies on the fact that we spent a lot of time at the beginning understanding the first material. The other important part of understanding this process is that we then understand the reactors that we use to make the films. And because we understand in the lab these relatively small reactors that are, say, 200 millimeters in diameter that are able to do one coating at a time on a small piece, we then can model that reactor. This is a cross-section of the reactor, and this shows the velocity profile. We can take our knowledge of those velocity profiles and then do a scaling to larger reactors without having to do as much experimentation as we hadn't done the modeling. And this actually is the actual inside of a picture of a large-scale reactor that we have at MIT. It's 300 millimeters wide, and it works in roll-to-roll processing, which is really advantageous for getting the cost down and really is advantageous particularly for flexible electronics. So that gives you a little bit of insight of what the basic science is and what the drivers and differentiators are. Let me talk about how this has been commercialized. So the first polymer that we did was polytetrafluoroethylene, which is better known as Teflon, which is the DuPont trade name, sometimes called the king of polymers. And it's insoluble, so it's hard to do from solution. But one of the amazing properties that it has is lubricity. The PTFE chains just slide across one another, and it's also very chemically and thermally stable. So while you may be able to buy, say, non-stick cookware, which is treated with Teflon, there are many other applications that Teflon would be good for that the process, traditional process doesn't address. Particularly, it's so-called spray and bake, and you really need to go to high temperatures to get the material on. And it's also very difficult to coat these complex geometries. So to commercialize this vapor technology, founded a company called GVD right next to MIT in Cambridge, and the research and development is there. And then we also started a manufacturing concern in South Carolina because that was next to our major customer. And two of my PhD students are really leaders of the company. Hilton Price Lewis is the chief executive officer, and Shannon O'Shaughnessy is the CTO. So that's an example of people really being the means of tech transfer. So the business model is primarily to provide coding services. So people send us a part, we code it, they pay for the coding and send it back. We also have a licensing model, but the coding services model is the predominant one. We've entered two different markets. One is in semiconductor parts, where the lubricity that you apply to the pieces that build the semiconductor equipment is essential for their operation. And what I will share with you more today is the use of this actually for rubber manufacture, particularly for tire mold manufacture. And with government funding, we are continuing to look at additional applications for this PTFE coating. So this is a picture of the manufacturing facility in South Carolina. We have a van which actually picks up the parts from our main customer, brings them to the building for coating. This is a picture of the website for the company, and you can see that we're really interested in the molding of tires. So the GVD product for this is called Rapid Release. It's based on this PTFE vapor deposition technology that was developed and patented in my lab and licensed to GVD. And the benefits this brings is that if you're thinking about molding tires, you definitely don't want tires to get stuck in the mold. And the way that people prevent that now is through solution processing. So here's a worker spraying on, which is something which is typically a silicone oil, to the tire. So there's several problems with this. There's environmental problems. So you see that the worker is protected against this spray release into the environment. And also that it needs to be done every few cycles. In this case, it's showing every 4 cycles, every 4 tires you make, you have to spray this. And the spraying is non-precise. What's happening is a person is spraying it, and they may do a different job of applying the spray in one case than the other. What we're doing here is taking one of these CVD reactors, which is so well known for its uniformity and reproducibility in the semiconductor industry, and putting an entire tire mold inside so that we can coat it. And this is a complicated process, but it's one that lasts. It will last through the entire season of molding tires. So we get over 1,000-fold increase in the durability of the coating by the vapor deposition method rather than the solution method. And here in this picture, you see the benefit of having this coating. At the top is the coated tire mold after many cycles of tire molding. And you see that it remains quite clear. Whereas without this coating, what happens is that the carbon black from the tire rubber actually accumulates and eventually causes the tire to stick and disrupt the entire method. These are pictures of the reactors here, large scale, that were developed. And this brings really improved manufacturability. I see that my time is running down, so you'll have to apologize for me going a little bit quickly through the next examples. We're also bringing the vapor deposition process to the problem of energy and particularly condensation of steam. And as you might know, when you produce electricity, much of this has to do with steam turbines. And while we get 32% of useful energy out of the condensation of steam, we're really wasting a vast majority of it. And it's the idea of just simply a coating can improve that efficiency. And really, when you go through the energy cycle, the condensation of steam is really a bottleneck in this. So how can we make steam condense more efficiently? So here's a cross-section of the power plant. The turbine is really what generates the electricity, but the steam that's the exit from the turbine needs to be condensed. And this is condensation step is what we're going to discuss today. So if you look inside this condenser, there's tubes, and on the outside of those tubes is where the steam is. We have cooling water on the inside. And really our technology is about coating the outside of those tubes so that the steam will condense more efficiently. In the current conditions, the steam condenses and makes a film of water. And this water is really an insulating blanket, and it prevents the subsequent steam from condensing as efficiently. If we have a hydrophobic coating that maintains the water instead of as a film in dropwise mode as shown here, the heat transfer remains high. And here we actually show the ability to get the heat transfer coefficient to be efficient. Here's where the current operating regime is, and here's the improvement with the hydrophobic coating that's being commercialized by Dropwise technology. And in addition to improving the heat transfer, it's also a durable coating. So let me just show you some movies of I'm not sure why that didn't play. I apologize for that. But the idea is that even after 48 hours of accelerated testing, our ICVD film did not actually come off, where other technologies are not as durable. So it's important to think about not only performance, but durability. The final thing that I'd like to leave you with is some technology that allows you to make devices on ordinary